So now first let's implement this function, the init function of our RTC chip. Here first we will initialize the I2C pins. Here first we will initialize the I2C pins. After that we'll initialize the I2C peripheral. Let's do these two steps. So I'll create a helper function called DS1307 I2C pin config. So now it's a static function, actually, a helper function to initialize the I2C pins. Let's implement that at the bottom here. So it doesn't return anything. You can keep it as static. So here we have to initialize the GPIO pins for alternate functionality. And the alternate functionality is I2C. I have created two variables of GPIO handle underscore T, and all member elements are mem set to 0. Here SCL is PB6 and SDA is PB7. First let's initialize the SDA. Let's initialize SDA. GPIO port is equal to the port what we have mentioned in the header file of this chip. In the header file we have written this one, DS1307 I2C GPIO port. Let's use this macro. So if application wants to use some other GPIO port, then the application can make a change here. Let's initialize that here. After that, I2C SDA GPIO pin config alternate function mode is equal to, we know that it is 4, and I2C underscore SDA, and after that the pin mode is equal to the alternate function mode, isn't it? GPIO mode alternate function. I2C SDA GPIO pin config pin number is equal to, what's a pin number? Again, you have to use the macro here, pin number for SDA, which is this macro you have to use. So you know that output type is equal to open drain, and after that the PUPD control is equal to, again let's use the macro. So I2C PUPD, let's use internal pull-ups. Later we can change it to external pull-ups, but let's try with internal pull-ups. That's why I say GPIO no pull-up or pull-down. I'm sorry, here GPIO no pull-up or pull-down. So we are not using internal pull-ups. That's why what I would do now is I'll just change this to pin pull-up. Let's try with internal pull-ups. So DS1307 I2C PUPD, which is set to internal pull-ups. After that, and speed you can set it to fast. Let's call GPIO init, and you have to send the address of this variable, that's it. And let's do the same thing for SCL. You can just copy paste this one, change everywhere SDA to SCL, and here this is SCL pin. That's it. So we finished our first task here, and let's give the prototype of this function right here. And after that, let's do the second part, initialize the I2C peripheral. Now for this, let me create I2C handle variable. Let me create that here, I2C handle underscore t. It's a global variable. I call it DS1307 I2C handle. Now let's create one more helper function. Let me call it DS1307 I2C config. Let me just make it as static void. And here let's configure the I2C peripheral. So handle, let's first select the I2C peripheral. Here P I2CX is equal to DS1307 I2C. Right, so which is set to I2C1. And after that, I just initialize the config part here. The ACK control is enabled and speed is set to I2C speed. The I2C communication speed is set to standard mode. That's it. And after that, just call I2C underscore init, and that will initialize the I2C peripheral for standard mode. So let me call this function from here. Let me add some header files here. Let me add stdin.h and let me add string.h. This header file is for a fixed width data types, and this header file is for providing the prototype for the memset function. So if you go inside ds1307.h, then you have to include this header file, because we have used these macros, so which can be resolved only by including this header file, isn't it? After that, in the init function, let's enable the I2C peripheral. For that, we have I2C peripheral control. Here you should mention the I2C peripheral, that is DS1307 underscore I2C enable or disable macro, so which is enable. After that, from the data sheet of this chip, so we know that initially the oscillator will not be running, so the timekeeping function will not be running when you first give power to the RTC chip. That's what written here. You have to make CH bit as 0. So the internal clock is halted when you first give power to the RTC chip. So the internal clock will start running only when you make CH is equal to 0. Let's do that in our init function. So we'll make CH is equal to 0. If you want to make CH is equal to 0, then you have to communicate to this address 00 through I2C communication. That means we have to now write into this address. So now let's understand how to write into different addresses of this RTC chip. For that, in the data sheet, go to I2C data bus section here. And here they have explained, just browse through this document. You see here they have given some figures by which you can understand data write and data read. Now we have to implement data write. We are going to write some data into slave's register. That means master is going to write and slave is going to receive, the slave receiver mode. These are the things you have to do. First, master should trigger the address phase. You already know this, start condition followed by the address of the slave, and then the read write bit is set to 0 because master is going to write. This is the address phase for which slave acknowledges here. After that, the master has to write the address to which the master wants to send data. Here the master should send the address first, address of the register. Remember that. Once the address of the register is sent to slave, slave will tune its internal address pointer to this address. Don't get confused here. This is a slave's address. This is a register address. Before writing, you must tell the slave to which address master wants to write. That's the reason master first should send the register address, for which slave sends ACK here, and after that master should send data. This data will go into this register address of the slave. So this is the first data byte which is sent by the master, for which slave acts here, and then master can send any number of data, and when master has no more data to send, so the master can simply raise the stop condition. Very simple, isn't it? Now we have to do this part. So we have to write 0 into the register address 0. So now our job is to write 0 into this register address. The register address is 0. Now let's do that. So let me just mention the fourth step as make clock halt is equal to 0. For that, I'm going to write one simple helper function. Let me call it as DS1307 write. To write, I need address and the value. Let's send two arguments to this function. First one is value and second one is address. Address means register address. So the value we know 0 and the register address is 0. That is seconds address. We have a macro for that, DS1307 ADDR underscore seconds. So now let's implement this function, right? So somewhere down here, so let me make it as static void, and here this is value. Let me call it as uint8 underscore t value, and this is uint8 underscore t address or reg address. Here let me just create one array. So let's say tx of 2 bytes. In tx of 0, I'll keep the reg address, and tx of 1, I'll keep value. And after that, we have our function I2C master send data. Let's do that. So handle, which is this one, buffer is tx, length is 2 bytes, and the slave address is DS1307 address. Or do we have slave address? So let's see what is the address. This one. Let's use that macro here, and repeated start you can make it as 0. What this function does, first it generates the address space on this address, and after that it sends the first byte, which is the register address. So exactly like this diagram here, our function first generates the address space, then it sends the register address, and after that it sends the data. The data in this case is value. That's it. We made clock halt is equal to 0. Now let's read back. Fifth step is read back clock halt bit. If it is really set to 0, then we can conclude that the initialization was successful. But if the clock halt bit is not set to 0, then we can conclude that there was some problem. So we can conclude like initialization has failed. For this, I'm going to implement another helper function 1307 read. For read, you have to just send the address. So from this address, we are going to read back, and let me create one variable here, uint8 underscore t clock state or something like that. Clock state is equal to, now let's implement this function now, read. Let me just copy this function here. Let me make it as read from the register address, and let's remove all these things. Now we have to understand the data read. Master wants to read, that means slave is in transmitter mode. So very simple, you already know this, that master has to trigger the start condition, the master has to trigger the address space with read write bit set to 1. So slave acts here, and after that slave will start sending the data. Slave will start sending data from which address? Remember that slave will start sending data from the address to which its address pointer is currently pointing to. That means before you do a data read, you must first initialize the address pointer of the slave by using data write. This data is coming from the address to which the slave's address pointer is currently pointing to. That's why that they have mentioned in figure 6 actually. You can take a look here. This is how you should do data read. So first master has to initialize the address pointer of the slave by using data write. This first part is data write. Here you can see that read write is set to 0. So master first writes the register address with no data, for which the slave acts here, and after that master immediately triggers the repeated start, or master can generate stop condition here and it can again trigger the start condition, no problem, or repeated start, one the same. Here master wants to read, that's why the read write is set to 1, and slave acts for that here, and slave will start sending the data. That's why in our code we'll do this. Let me first do a data write. So I2C master send data. This handle buffer is nothing but, there is no buffer, I'm just sending the pointer to the register address. Length is 1 byte, slave address is this one, repeated start is not required. Let master generate the stop condition. I am doing this to accomplish this part, and after that let's trigger I2C read master receive data. Handle, we have to receive 1 byte of data. Let me just create one variable called data, and here I can mention it as data, the address of data variable, length 1, slave address is this one, and repeated start 0. That's it, and just return the data. That's it. Let me give the prototypes of these functions. So let's give the prototypes here. That's it. And after that, here clock state. So now here let's return the clock state. Return clock state of, let's shift this by 7, because the clock state is bit number 7, right? So let's return the status of that to the application. Let's do a bitwise AND with 0 cross 1. If this function returns 1, that means ch is equal to 1. So if it returns 0, then ch is equal to 0. So we can conclude like init failed in this case, because the readback was showing 1, isn't it? For ch, something went wrong. So we can conclude like init failed. Here we can conclude like init success. We just implemented the init part here, and now let's implement the set current time function. So before that, let's try to compile this. Before compiling, make sure that all these header files exist in your code, and this looks fine. And in the 017 RTC underscore LCD.c, that's our application, just write the main function. Let's compile. There seems to be some problem. Let's address it. So it says implicit declaration of function I2C config. What's wrong? The prototype has not supplied. So let's do that. Here, give the prototype. Let's compile. The read actually is not void. It is uint 8 underscore t. This is uint 8 underscore t. Let's compile once again. It looks fine. Complete up to here. I'll see you in the next lecture.